All right, let's look at more issues with these nuclear reactions. Uh, let's look at transmutation. When we can take elements that we know, slam them together, and get new elements. 1940 was our first transmutation. Neptunium was synthesized. What happened is scientists took uranium 238, bombarded it with a neutron, and that turned into uranium 239. And over a half life of 23.5 minutes, it decayed into neptunium 239 and gave off a beta particle and an antineutrino. This neptunium 239 then decayed into a plutonium 239 over 2.4 days. And that gave us our second transuranium element. They're called transuranium because we look at the periodic table. Here's uranium, and they're above uranium. There's neptunium, there's plutonium, and all these guys right here. And when you look at the names of these guys, you kind of can get an idea of where this was happening. Neptunium, plutonium, actually named after the planets that were discovered around that time, Neptune and Pluto. But AM is americium, curium, Marie Curie, berkelium, California, californium here. Einsteinium, fermium, as in Fermi lab, Mendeleev table, nobelium, lawrencium. You might have heard of these words, some of these before, because most of these came from the Lawrence Berkeley labs in California. All right. And it turns out one of the major pioneers in all this work is a physicist by the name of Glenn Seaborg, and we actually named element 106 after Glenn Seaborg, Seaborgium. But Seaborg is one of the people responsible for coming up with most of these transuranium elements. All right. Now, so we made a bunch of them, and what can we do with them? Well, not much. They have extremely short half-lives. They only last for microseconds or less, a lot of them. Occasionally you can get one existing for a longer period of time, but they're extremely short half-lives. In general, we look at what happens when we smash the particles together. We can take things moving at roughly 9/10 the speed of light in our particle accelerators, smash them together, and we say, oh, based on what I see here, this element must have existed for an extremely short amount of time. So at this point, there's no way to really capture them and save them. They just decay too quickly. But who knows what the future brings. All right. Our last part of this chapter is radiation and health. And we'll just go through a few terms, and then we'll show you, okay, what you have to worry about, and then how this radiation can help you. We will end this chapter instead of evil of bombs and stuff. We will end this chapter with good. How we can use radiation, how we can use nuclear reactions to make our lives better in terms of our health. All right, so a few things first. RADS, the radiation absorbed dose. This is the amount of energy due to radiation. This is alpha particles getting hit by alpha, getting hit by beta, getting hit by gamma particles. How much energy due to radiation absorbed by living tissue? 1 rad means 0.1 joules of energy absorbed per kilogram of tissue. So rads is a way to measure energy, but it's how much energy a kilogram of tissue is going to absorb. That's not necessarily how much energy was given off by the radioactive object. If you've got just a lump of uranium-238, how much energy is given off by it? That's usually measured in curies. 1 curie is 3.7 times 10 to the 10th DPS, disintegrations per second, which means if a lump of radioactive material was given off 3.7 times 10 to the 10th beta or alpha particles per second, that would be 1 curie. All right. Note 1 picocurie is about 1 times 10 to the minus 12th curies. And usually when we're looking at the amount of energy given off just by like uranium-238, it's in the picocuries. So it doesn't give off that much radiation. Uranium-238 doesn't, which is good because we find it in our walls and stuff like that. Okay, so Curies, the amount, and you'll see there's other ones like grays and things like that. Curies, the amount of energy given off by this radioactivity, the amount of radioactive stuff given off by this radioactive element. Rads is how much you absorb per kilogram of tissue. 1 rad is 0.1 joules of energy per kilogram of tissue. REMS is the Rontgen equivalent in MAD. It's the different, because different forms of radiation do different amounts of damage, because, yeah, we want to know how much energy is being given, you're absorbing, how many joules of energy absorbing, but different particles give off do different damage. And so it's a very quick calculation. The number of REMs, how much damage is done, equals number of rads, how much energy is absorbed per kilogram of tissue, times a factor, a kind of a badness factor, how bad it is for you. Now, this factor for a beta particle, this factor is 1. So 1 rad of beta particles equals 1 rem of beta particles. Gamma is 1. So 1 rad of gamma particles equals 1 rem of gamma particles. Alpha is 20. 1 rad of alpha particles gives you 20 rem of alpha particles. What this means is, and note this is inside the body because alpha particles are blocked by your outer layers of skin, but if you intake alpha particles, they do 20 times, 1 alpha particle does 20 times the damage as a beta particle or a gamma particle. So, alpha particles inside you do very, very much damage. To this day, I do not eat Alphabets cereal. Yeah, come on, Alphabets. All right, so, but what type of damage do you get just by doing normal daily activities? Well, your book has a pretty good table on that. And when we look at this, the first thing to note is not this top table. I think they did it wrong. Is this bottom table here? That's one of the important things to look at. Is when we look at this bottom table, we see, okay, how much REMs can you absorb and do damage? Well, if you get between 20 and 100 REMs, that's going to give you, some problems here. Decreased white blood cell count, possible increase in cancer. But, just decreased blood cells. So that's not too bad. 20, 50 REMs up to 100 REMs. Not too bad. I wouldn't want to deal with it, though. 100 to 400 REMs, well, now you start getting radiation sickness, vomiting, nasty lesions, all sorts of nasty things, increased cancer risk. 500 REMs, death, and it'll take you within 2 months. So you get a dose of 500 REMs, you're going to die in 2 months. 1,000 REMs, you're going to die in 2 weeks. 2,000 REMs, you're dead in an hour. And so that's the deal here. So the thing is that your body can repair itself. If you get 20 REMs, that's going to be bad for you, but over time your body can repair that damage. You get to 500 REMs, your body just can't repair the damage fast enough, and so you die. So what types of things, normal activities, give us what type of how much REMs? And realize that we're really looking for 20. Below 20 REMs, we're not going to worry about it too much. Well, when we start with natural radiation here, a 5-hour plane ride, because you're up higher in the atmosphere, there's less atmosphere to block some of this natural radiation. You get a little more natural radiation. So that's 2.5 REMs per trip, or no, 2.5 millirems. Note a millirem is 1,000th of a rem. So if 20 REMs is what we're worried, it was when we really start to worry, when we get 20 REMs, 10 REMs is a little bit of worry. 20 REMs is when we start really worrying about, ooh, this is getting nasty. This is 2.5. This is 1,000 times less. So you get 1,000 times less REMs flying in an airplane than worrying. Oh, this is 20, so it's 10,000 times less REMs. So we don't worry about it. Our body can repair any damage here. Outer space, terrestrial radiation, stuff like that. Note radon gas. We discussed radon gas, 200 millirems per year, and that's just if you don't have extra. If your basement doesn't have high levels of radon, this is just normal levels of radon. So yeah, high levels, this becomes a bit of a problem because we're at 200 millirems. 10 times that, we're up to 2 rems, and that's getting closer to 20. Chest x-rays. No, the chest x-ray, 8 millirems. Not a problem here. You get a whole body chest x-ray, that is much less. You get that once a year. That's much less than you just get from the ground. All right. Dental x-rays, all this other x-rays here are all in the millirems. We don't worry about it, but we're starting to tick up here. Gastrointestinal thing. Note, as we get into CT scans, a CT scan is actually a whole bunch of x-rays. A whole body CT scan is 200 millirems. Okay, I'm dealing with that. But that's just of the head. If you get a body, abdomen, or pelvis CT scan, which are quite common, that's 1,000 millirems. That's 1 rem. One abdominal CT is 1 rem of radiation. I'm not going to worry about it if I get 1 CT scan a year or every couple years. But doctors will not give you multiple CT scans. They're not going to give you a CT scan a month, because 1 CT scan of the abdomen a month gets you up to 12 REMs, and then we start to worry. So you can't just throw someone in a CT scanner. You have to think about that. And note building materials and stuff like that, 3.5 REMs. But when you look at this list, yeah, the CT scans, we worried about this. But what gives you the maximum amount of radiation? Smoking. If you smoke 30 cigarettes a day, I think that's a lot, but I'm not a smoker. I don't know. If you smoke 30 cigarettes a day, that gives you 16,000 millirems a year. 16,000 millirems is 16 rems. We are awful close to 20. So 2-pack-a-day smokers are really in danger of increased cancer risk and increased white blood cell count, which means you can't fight disease as well and stuff like that. So, take-home message here. Do not worry about natural occurring radiation. It's just not enough to hurt you, except radon gas. Make sure your basement's clean. Make sure you got less radon gas than the maximum limit, or get the radon remediation thing. It's kind of cool. It works really well. Don't worry about chest x-rays. Don't worry about a CT scan unless they're saying, oh, we need to give you 10 CT scans. Hold on, dude. That's a little excessive. All right. The biggest problem is smoking. Don't smoke. And what's really going to mess you up is if you smoke a lot, so that you have to get a lot of CT scans of the chest, and you live in your basement and there's high radon levels. That would be just super nasty for you. Don't do that. Okay. But let's look at good, because it turns out people found that, you know what, if we actually put some radioactive elements in the body, we can kind of trace what's going on. And so we can use this radioactive elements for diagnosis. For example, it turns out that your thyroid is responsible for regulating iodine in your body. Iodine collects in the thyroid. When you had the Fukushima reactor accident in Japan, and anytime people are worried about radiation from the air, they are often asked to take iodine pills, because if iodine collects in the thyroid, and if this iodine that comes from nuclear reactions, if you breathe that in and it stays in your thyroid, you get thyroid cancer. So you want to take these iodine pills that'll help push out any radioactive iodine that might be in your body, to to avoid thyroid cancer. But if we inject you with a little bit of iodine 131, just a little bit, it'll collect in the thyroid, and then we can see when we examine your thyroid, we'll look at it and see if how much radiation is coming off. If there's a tumor in your thyroid, it will show because the iodine will not collect in the tumor or something like that. And so we can inject your body with various different compounds and then monitor where the radioactivity is coming from. And note, we are going to keep the radioactivity very low. We're not going to inject you with something that's going to give you 16,000 millirems of radiation. But we inject this in you, and then we can see where it goes. And through gamma, beta emission, electron capture, we can examine what's happening. Interesting thing, fluorine-18 is a positron emitter, the antimatter particle positron, and it just collects in. If you put fluorine-18 in with some glucose, the glucose will travel, and then wherever the glucose is being used, it'll give off these particles. And so here's a picture, a PET scan of some positron. PET scan is positron emission. And wherever the brain was really using glucose, really thinking a lot, that lights up because the more glucose it's using, the more glucose is in that area. Since we put positrons in there, the positrons are being emitted from there. Well, we put in the fluorine-18, which emits positrons. Cool. So that's good news. With small amounts of radiation, small amounts of radioactive isotopes, we can put them in your body, and we're not going to worry that there's small amounts, natural nuclides in the body. We're not going to worry about these procedures because they're very, very low in the REM count, but we put these radioactive nuclides in your body, and then we can tell what's going on with you from the inside without having to cut you open, which I think is a good thing. So let's end this chapter on good things like being better and, let's not smoke and get CT scans in your basement.